Welcome, everyone. Let's begin.
He has a sick leave.
Yeah, I've already seen
He
it.
gave it to me and he told me to show it to you.
Okay, thank you. Just grab the in-class exercise and notes. You can go through the homework assignment after class. All right. I've received all the homework assignments, the writing center appointments. As I've been getting the emails, I'm updating the grade book. So the deadline for that is 5 o'clock today. And then next time when we meet here in this classroom during our normal class time, we're going to have exam 2. At the end of our class period today, we're going to go through some concept questions just to maybe kick off your review for that exam. So we'll do a little bit of prep for that. As a reminder, you can prepare an equation sheet, both sides of a paper, but it can only be used on the second part of the exam, which is problem solving. You're not allowed to use it during the concept questions. Today we're going to talk about disinfection briefly and spend most of our time discussing how sludge is treated and disposed of. Any questions about the announcements before we move on? Starting with you in the back. Excuse me? From the last exam until now. So the material, it's including today's class. That's right. Sure, I'll do that. I'll post the solution on iLearn for today's assignment. Yeah. Any other questions? If I forget, send me an email. I'm pretty forgetful. All right. Let's talk about disinfection. There are some similarities between wastewater disinfection and drinking water disinfection. We can use either chemical methods or physical methods to do that. And by far the most common disinfection method that's used these days is chlorine. And it's just mainly because that was the first disinfectant, and there's the inertia of once you've got something, you tend to stick with it when you've made the investment to purchase all of the equipment. It has a lot of problems though. People are starting to switch away from chlorine. One of the main reasons is because of the risk. You can see this photo here. There's someone here wearing a biohazard suit. Working with that much chlorine gas, which is a very strong oxidizer, threatens not only the people who work at a wastewater treatment plant, but the people who live nearby. Chlorine is usually delivered in 1-ton cylinders, and so 1,000 kilograms of chlorine, if it breaks open, could expose several kilometers radius worth of people to really harmful conditions, and there would have to be an evacuation plan in place anytime chlorine gas is used. The people who work at the treatment plant have to be specially trained to deal with a breach of a chlorine cylinder. So a lot of people don't want to have to worry about the planning and the upkeep of all that risk, and so people are starting to move away from chlorine. It's dangerous, it's costly. The chemical itself is relatively cheap, but what's expensive is the training and the insurance that has to go with the safety risk and so on. Another problem with it is that chlorine is most effective against bacteria, but there's other things besides bacteria in wastewater. There's also viruses, there are protozoans and cysts, and so the chlorine doesn't kill everything we need it to kill. It can cause cancer through disinfection byproducts. That's something we've talked very briefly about before. But then also, chlorine itself is toxic to fish. And remember, this water isn't going to people. This water is going to a river. And so if you add chlorine right before the water gets into the river, then you're damaging the ecosystem that receives that chlorinated water. And so for that reason, there's actually another step after chlorination called dechlorination. And so you're having to add not only chlorine, but another chemical, usually sodium thiosulfate, to dechlorinate. So it's just complicated and expensive, and so UV and ozone, which are alternative disinfection methods, are getting to be a little bit more popular. UV, for example, avoids many of these risks. It avoids many of the safety risks. It can inactivate the pathogens that chlorine will miss. UV itself isn't toxic to fish. The only concern is that the lamps that go into a UV reactor, there would be little tubular lamps similar to these. These are fluorescent lamps, but they have mercury in them. I didn't know, I don't know, maybe you've broken open one of these lamps before, but once you do, it's actually a dangerous thing because there's trace amounts of mercury, which is poisonous to people. So the risk with this is if the lamps are broken and that mercury gets into the water. It's probably less catastrophic than a chlorine breach, but still, I guess there's nothing that eliminates all risk entirely. So that's disinfection. This is a photo of the wastewater treatment plant at University City. You got an email from Akil about our trip to the treatment plant. We're still working out when that's going to be, though. I think his hope was that we could do that on Monday, right? That's what he said in the message. But we have Tuesday classes on Monday, right? So stay tuned. We'll figure out when we're going to go to the treatment plant. When we do, that's chlorine in solution. Thankfully, we're not exposed to the risk of if it had been gaseous chlorine. Liquid chlorine is a lot less risky. The only problem is you have to use a lot more of it. Yeah, some students it's Monday, so we need to find a time. I think the following week there wouldn't be the same conflict, but we'll work it out. Stay tuned. Here's a picture of a chlorine contact chamber. This photo here is a plug flow reactor. Once you add the chlorine, you have to give it some time to work. And then you can just see there's a stream of water where they're spraying a little bit of sodium thiosulfate here to dechlorinate. And then the water goes around the corner, and it has some time for that dechlorinating chemical to act so that by the time the water here goes to the river, it had been disinfected and dechlorinated. There are a couple of different types of UV reactors. Sometimes the water will flow into the reactor and parallel to the lamps. You can see just a glimpse of the lamps here. The lamps are oriented parallel to the direction of flow. Sometimes the water will go through the reactor, and here the lamps are transverse, and so you're passing, the lamps are this way, and so it's perpendicular flow rather than parallel. Usually, if you have a perpendicular flow like this, you're using very, very high intensity lamps that are called medium pressure lamps. These lamps are low pressure, high output, and it boils down to basically electricity costs. If you have a low cost for electricity, you can use these higher intensity lamps, and then it makes things a little bit simpler. All right, so sludge. That's what we're going to spend most of today talking about is sludge. And there's a direct relationship between how many solids we're removing and also the amount of BOD that's removed and sludge. You've calculated P sub x, which is the mass of sludge produced. That's on a dry basis. But as I pointed out in the last part of the secondary treatment problem, sludge is usually mostly water. The sludge solids account for between 1% to 2% of the total mass of what comes out of the bottom of a clarifier. There's the dry component, which is the sludge solids, and then water, which is the majority of what's there. We generate a lot of sludge. If you know the flow rate of the treatment process, primary treatment is less than 1% of the total volume. Coming out of that is going to be the primary sludge. Activated sludge is a little bit more in terms of the volume of the overall process. And if you're using chemicals to try and remove phosphorus, like precipitating phosphorus, then adds to the volume of sludge as well. Sludge is really important because, like aeration, it is a costly process. Remember, in aeration, what made it expensive is we're having to use so much electricity to put oxygen into the aeration basin so that the microorganisms can breathe. What makes sludge treatment expensive is we're trying to get rid of water. If something is 98% water and you're trying to get rid of the water, then obviously you've got a problem because most of this stream is water itself, and we don't want to just take huge truckloads of mostly water to the disposal, the landfill. In fact, they don't really like it if you take wet things to the landfill, because then it could possibly leak through into the groundwater. So we have to find ways to dry off the sludge. When we go through sludge treatment, we have some guiding principles of what we want to do. We want to reduce the volume of it, because there are trucking costs, there are disposal costs, and those are all based on the volume of sludge. If we decrease the water content, then that will reduce the sludge volume. So if our sludge to begin with is 1% solids and 99% water, it may seem like it's not much of a change if we only make it 2% solids. It seems like you've really only changed things by 1%, right? 98% water. But actually, that's a little bit misleading, because if you double the amount of solids, what you've essentially done is you've cut the volume of the sludge in half, because you've separated the water from the solids. And so even a small increase in the solids percent has a huge impact of the total volume that has to be hauled away in a truck, or the volume that has to be laid out in beds for the sun to dry it. And so when we talk about percent increases in solids, they may seem very minor, but it has a huge impact. To go from 1% to 2%, volume of sludge is half, because you've doubled the mass of solids. Yeah. You can, but the sludge solids will clog the membrane very quickly. And so, that's what we're trying to do, is find out some way to get the solids and the water separated. If we use a progressive, increasingly small diameter pore sizes, then that can work. But if we take the sludge directly to ultrafiltration, then the issue becomes trying to get the membrane clean. Sometimes sludge has lead or mercury or chrome, other chemicals that are toxic to people and the environment, so we have to identify them and get rid of them. And sludge, of course, also has pathogens. And so if you're going to try and use the sludge somehow, then you need to kill the pathogens before you use the sludge as a fertilizer. And one problem here in the UAE that we have is that sometimes sludge is used as a fertilizer without neutralizing the pathogens first. Does everybody here know what jarjir salad is? Yeah. Jarjir, right? So there have been several articles in the Gulf News. A chemistry professor here on AUS campus has tested jarjir throughout the Emirates, and he's always finding bacteria in it because they're using fertilizer to grow the jarjir, and then it's not on the outside of the jarjir, but on the inside of it. So I still eat it, but I haven't gotten sick yet. But the pathogens, huh? I eat it a lot, but apparently it has pathogens in it. So it would be better, it would be more safe, probably our immune system would calm down a little bit if the pathogens were neutralized before they were using the fertilizer in that way. Okay. If we're working as engineers for a client, the number one thing our client wants us to do is minimize their costs. They don't want to spend too much on squeezing water out of sludge. It doesn't seem like an interesting or fun way to spend money, right? Squeezing water out of sludge. So we have to try and find the technology or the solution that can dewater sludge the most efficiently. The other thing is that when you're working with the sludge solids, you're putting air into contact with organics, and that can really cause a lot of odor issues. If you're way out in the desert, that may not be an issue, but oftentimes these treatment plants are close to populated areas, like the University City treatment plant is very close to where people live and work. And so we have to find methods that are cheap, don't cause too much odor, and if we can, we'd love to use the nutrients that are in the sludge, whether it be for crops or fertilizing grass, or there are other things as well, like using it as a building material. Here's the simplest thing you can do with sludge. is just put it into a big lake, a lake of sludge, and aerate it. This is letting Mother Nature take its course, basically just having the bacteria that will start to grow in a sludge lagoon break the sludge down aerobically. The purpose of this device is just to recirculate the sludge into the air and try and provide some aeration. This is a surface aerator, similar to the surface aerators that we saw for secondary treatment pictures previously. We can do a little bit better than that, though. Not every place wants to have a big lake of sludge nearby, right? This is maybe the simplest thing to do, but an easier way to treat sludge, first of all, is to squeeze it with a belt. And this is a photo of, think about if you have a fabric belt that's progressively getting closer and closer together. If there's sludge in that fabric belt, by squeezing it, the water will drain down through the fabric, and then the solids stay together, and then it sort of it goes over the edge and into a hopper that collects the solids. And this can be very effective at removing the water from the sludge. Another technique that's used is putting the sludge into piles like this and mixing it with yard waste like grass clippings or sometimes food waste, and then allowing the sludge to stabilize itself, because it will get very, very warm. If you have a heap of sludge solids like this, the bacteria and the food are going to generate heat, and it's kind of an interesting thing that it'll actually, the pathogens that are in a pile of waste solids like this will neutralize themselves as they break down the BOD and the carbohydrates that are in that, and the temperature rises. There's a shift in what kind of bacteria are there. At first, it's the bacteria that prefer cooler temperatures, but as they eat the food and give off energy, the temperature of the entire pile increases, and so that it starts to favor bacteria that prefer warmer temperatures, and they start to kick in, and it can be a pretty effective way of dealing with sludge solids. Now, this is way off the charts in terms of the technology scale. When we want to, we have a lot of sludge, and it may be a high concentration sludge, anaerobic digestion is a way of actually capturing the energy that's formed in the form of methane, capturing the methane gas, and in some places they're actually generating electricity from the methane gas that is formed when sludge is broken down by anaerobic bacteria. You can tell when you're at a wastewater treatment plant where the sludge digestion is happening, because usually the tanks are open to the air. Like we've seen clarifiers and aeration basins, and they're always just, the air is around them, the rain. If it's raining, it'll go into those things. But these have a roof on them. So if you see a circular tank with a roof, that's anaerobic treatment of sludge. So the pictures we've looked at with the belt press, that's a way of somehow trying to thicken the sludge by gravity or squeezing or flotation. Stabilizing is when you're trying to digest it, like in the photo that I just showed you of the anaerobic digester. You're trying to make it more inert, or maybe even recover energy. If we add chemicals to sludge just to help us so that we can separate it more easily, that's called conditioning. And sometimes we'll do flocculation, coagulation processes with dilute concentrations of sludge to try and get them to settle better in a clarifier. Dewatering can include using a vacuum, or if you pressurize the sludge to dewater it. Reduction is becoming less common because in the past sometimes they would just burn the sludge and allow the sludge solids to burn away, and the water component in the sludge, of course, will just evaporate. But it uses a lot of energy if you're burning something that's 98% water. And the other problem with it is if sludge has heavy metals, then you're putting mercury and lead up into the atmosphere. And so instead of doing these things too much, what we'd really like to do is find some way to recover the nutrients like phosphorus and nitrogen and incorporate the sludge into some beneficial use. Ultimately, no matter what we do, the sludge has to go somewhere. It either has to go into the water, the air or applied to the surface of the land. As far as water goes, sometimes they'll actually dump sludge into the ocean. That's pretty uncommon nowadays. That's a practice that maybe was more common back in the 70s. But now, water destination for untreated sludge isn't common. We still put the wastewater effluent into the water, but not the sludge itself. If we incinerate the sludge, then those components can get into the air. So land application is really what we do a lot of these days. And here's that picture of the Dubai municipality's fertilizer that they make out of sludge solids. And they're able to sell it and partially offset the cost of drying it. I don't know. I think this probably is treated, but I think sometimes farmers are using maybe waste products from smaller treatment plants, some of the smaller communities, or maybe they're just using the animal waste directly without. I'm eating giardia not every day, but a lot. I'll post a link to that article. It was in the Gulf News if you want to read more about it. Yeah. I haven't got sick yet. Not that I know of. All right. We want to make the sludge have less water, more compressing the solids altogether. And there's an interesting technical way to do that. It's called thickening. What you do is you have a tank that's pressurized. You're pumping the sludge into a pressurized tank. When you have a pressurized liquid, you can dissolve more gases in it than normal. Like if you have a can of Pepsi, you know that it's pressurized before you open it. But what happens when you open that can of Pepsi? The bubbles are starting to float up, right? That's what they do with the sludge. You combine some dissolved gases and the sludge, and then you depressurize the sludge, and the sludge floats to the top because the air bubbles, or whatever the gas is, the bubbles are sort of causing it to float to the surface. So think about if you had a can of Pepsi and there's also sludge in there. When you pull the top, the sludge would rise to the surface because the bubbles are floating it up. So this is a way of simulating that same process. And then the thickened sludge that rises to the top is sort of scooped off of the surface, and then the watery stuff from the bottom is drained away. It's an interesting technical way of pressurizing the sludge, injecting air that's dissolved, depressurizing, which is the equivalent of opening the can, and then those little tiny bubbles will cause the sludge to rise upward. And this is a good method of thickening the sludge. It works really well on activated sludge, and it can increase the solids percentage from, maximum usually in activated sludge would be 1% solids. You can get it up to 6% in a system that's really fine-tuned and working well. And so that would reduce the volume of sludge you have to dispose of by a factor of 6. Sometimes, if the sludge is dilute to begin with, we can just use a clarifier, another clarifier that's specifically for sludge. We may need to add coagulant aids to get the sludge to settle down better. This is usually used on primary sludge because the solids that come out of the primary clarifier are larger than the solids that come out of an activated, the secondary clarifier. The secondary clarifier has tiny little particles because the bacteria are the organics, and bacteria is much smaller than the sludge solids that settle at the bottom of the primary clarifier. We do. We want to increase the sludge concentration of solids. No, because if you increase the concentration of solids, what you're doing is you're separating the water and the solids. So let me illustrate, let me think of a way. If we have a cup, and let's say that we have a little bit of solids and a little bit of water. All right. So what we want to do, right now, let's just say, for instance, this is 1% solid, 99% water. If I find some way to get rid of the water, some of it, so I'm going to get rid of half of the water that's in there by thickening it. And so if I bring the water level down, now I have half the volume of water but the same amount of solids. And so now it's 2% because there's the same solids but just less water. And so, you know, the percentage is the mass or the volume, mass of sludge relative to the mass of water plus sludge. Okay, so if we reduce the amount of water, it increases the percentage.
So the sludge itself, the mass didn't change.
The mass of the solids didn't change. But remember, sludge is two things. It's solids, a little bit of solids, and mostly water. So if we can get rid of some of that water by drying it out, by vacuum separation, by heating it, whatever, if we can remove some of the water, it increases the percentage, and then that means that there's less volume to dispose of. I'm glad you asked that question. Any other questions before we keep moving? Yeah.
Can we use it in another process?
Well, you know, we used it in the aeration basin as much as we could to seed that process, you know, to activate the aeration basin, but we have to dispose of some of it. You know, we can't keep recycling all of it or else it'll accumulate in the treatment plant. So we have to have some of it that we're drawing off and disposing of. So, you know, we can reuse it for fertilizer or we can incorporate it into bricks. That's one thing that they do is they mix the sludge along with clay and water to make bricks, but we don't have too many options for what to do with it. Here's a look at a clarifier where you could put either the wastewater and try and get it to settle, or if you have sludge that's relatively watery, this would be another way of trying to increase the solids content, is just give it a location for it to gravity separate. Adding chemicals can help the separation process. Coagulants, remember, what they do is they destabilize particles. Small particles that would normally repel each other, by adding a coagulant, that allows the particles to get closer together and then they settle more effectively. So ferric chloride. There are other things beyond just the normal coagulants. We can make chemical adjustments to the pH that can help the settling performance of sludge as well. And if you heat up the sludge, if you boil it, you'll lose some of the water through evaporation, but even just by boiling, it changes the nature of the solids particles so that they are able to settle more quickly. So that's another option, is the heat treatment. Okay, digestion, that building I showed you the picture of with the roof on top of the building, what we're trying to do is break down the sludge. Now, aerobic digestion isn't as common as anaerobic digestion for sludge because it requires so much oxygen. It would be really expensive to break the sludge down aerobically because of the electricity costs. And so rather than bother with that, what we'll do instead is anaerobic digestion. So let me draw attention to the difference in the word here. Aerobic means with oxygen. So you can break down the sludge by just keep giving it more and more oxygen. But remember the concentration, what was your X concentration in the homework? It's like 2,500, right? That was the concentration in the aeration basin, and in the sludge waste, I think the concentration was maybe around 11,000 milligrams per liter. So it's going to require a lot of oxygen if we break it down by just keeping to add more and more through a diffuser. So rather than do that, there are bacteria who don't need oxygen. They breathe other things. Rather than breathing oxygen, they can use carbon. And so anaerobic digestion is letting the bacteria that don't need oxygen break down the bonds in that carbohydrate that we're trying to dispose of. And it's a two-step process. You don't have to know all of the chemistry. That's more of like a graduate level thing to understand all of the chemistry behind anaerobic digestion. But just to give you a glimpse of what's happening is that the fats and the complex waste components like proteins, polysaccharides, they're turned into alcohols, and then the alcohols are turned into methane. And so methane is the ultimate end product of anaerobic treatment, and that methane is what can sometimes be burned to generate electricity. Much of the methane they'll turn around and burn just to heat up the sludge, because if you have hot sludge, then the bacteria act more quickly. And so sometimes it's used to recover energy, but sometimes it's just turned right back into making the process work more quickly by heating it. This is a diagram that shows one way of having anaerobic sludge digestion is you put the sludge into a tank, and over time, if you leave it alone, what it'll do is it will separate into layers. Not because only of gravity separation, because the bacteria that will break down the sludge, when they die, they settle to the bottom, and the bacteria that are alive and still using the BOD are here in what's called the active layer. But then above that is something called a supernatant. And the supernatant is clean, relatively clean water. It's much cleaner than the sludge that came in. And this takes about 1 month to 2 months is how long the sludge is inside of this tank before it goes out. And this is a continuous process. This isn't a batch process. There's always a little bit of sludge coming in and a little bit of sludge going out. So this is unmixed. And that's why it stratifies. Another combination is to actually mix in the first stage, and that speeds things up if you separate it into 2 stages, because normally the first stage happens a lot quicker, and we're always waiting for the second stage, which is the conversion of alcohols into methane. But if you separate the 2 processes completely and mix the first, then it can lead to an effluent from the first stage that is broken down more quickly. So instead of 1 month to 2 months, this high-rate digester can take between 10 and 15 days. So that's the advantage of having the 2 components separated, is it speeds things up. What we will see when we go to the University City treatment plant is they're dewatering the sludge by just drying it out. This stuff has a funny name. It's called sludge cake. It's a cake you never want to eat, right? But you're just letting the sun do the work of evaporating the liquid, and what's left behind is a material that could be used for fertilizer and have the nutrients recovered. It's just dried out over a sand bed. Mm-hmm. Well, it depends on where you live. If you live in Oslo, Norway, where it's cold and there's not much sun, then it would never dry out. Here in Sharjah, it's been 7 years since I was at that treatment plant, but I seem to remember they leave it out for like 3 months or so. Yeah, it's fairly quick. Yeah, when it's hot, any water that's laying out in the sun isn't going to last long. Right. You'll get an idea of that by how many beds they have. Like the space that it takes. We could look on a Google Maps, a top view of the treatment plant, and so this room, the area of this room, I think they have probably about 4 times the area of this room as drying beds. Yeah. Oh, you mean the volume that goes into the bed versus what's left? Uh-huh. Right. I may not be following your question. Maybe we can talk about it later. Basically, the depth of the bed, that's the volume that goes in, and what's left is only going to be a very small layer of the dried solids. But I don't remember what the flow rate is to the university treatment plant. I don't know what their Q in. Mm-hmm.
So usually it's 2% solid.
Roughly in the sludge.
It's like a lot bigger.
This is after it's dried. So this is after the sludge has dewatered. And so there's a lot of volume here that you can tell the water level was much higher than it is now. And so it started out as 98% water, but the water is evaporating, and so the level gets lower and lower until it's just the solids that are left. If we are dewatering it, we have to be mindful of the fact that there are limits on the heavy metals that can be applied to land. If you're spreading it out over an agricultural field, there are environmental rules that says how much chromium, how much copper, how much lead is allowed to be in sludge solids. And this is the last thing I want to show you, is just if you use sludge as a building material in bricks, it's actually a very good thing, because if you are taking bricks and putting it into a furnace anyway, which is what you have to do to cure bricks, then it's a way of inactivating the pathogens. And it also has a beneficial ability to reduce the weight of the bricks, because the organic material, what we're zooming in on, it's little voids, where when you heated the bricks, the organic material burned away, and what's left behind is a more porous brick, which can be an advantage if you're trying to make lightweight bricks. And so sometimes the sludge will be mixed in with the clay and the water at a brick factory, and it's extruded and then baked, and it just leaves behind sort of a very porous brick. Well, brick isn't always used as a structural material. Sometimes it's used for walkways, or it's used in decorative. So definitely, you'd want to use this not as a load-bearing brick, because it would make it weaker. Okay, everyone has the in-class exercise, right? Okay, we have 11 minutes. What I'd like you to do is read all the questions before you start writing any answers. Just familiarize yourself and pretend like today is exam day. Now it's not. Today isn't exam day. No matter what you write on here, as long as you write something, I'm going to give you full credit for being here today. So you don't have to worry about doing it right or getting it wrong. It's low stakes. But I wanted to give you an idea of basically what kind of questions you can expect for the exam related to this material. And so in a few minutes, I'll show you my answers. All right, question 1. Name a chemical and a physical disinfectant commonly used in drinking water treatment. Chemical, chlorine, physical, UV. All right. Anything else? Ozone? Okay, good. That's right. Which one? Bromine? I don't know if anyone is, although that is one of the halogen gases. I don't know of a place that's actually using bromine. Is it really? Oh, maybe they are. Yeah. Okay. Non-point source pollution. Agricultural runoff. It could be anything basically other than point source pollution, which is when a pipe goes into a river. Remember, the difference is whether it's flowing over a sheet or if it's coming from a single location. It should be like a factory or a pipe. All right, question 3. How is sugar non-toxic? Well, it all has to do with the bacteria and what they're doing with the sugar. Right. Increases the oxygen demand, which will decrease the dissolved oxygen, which is really the problem. Is it's going to harm fish, for one thing, but when the water becomes anaerobic, there's other types of bacteria that kick in, and they'll start making methane, they'll start making hydrogen sulfide. The things that anaerobic bacteria make are nasty. They're not good. So you don't want to live next to a river that has no dissolved oxygen, because then the bacteria will take over that are just going to really make unpleasant conditions. Profundal zone. Anybody remember what that means? Good. Light penetration, right. So plants don't grow there because there isn't enough light in the profundal zone. I'll post a PDF of this online, by the way, along with the homework assignment solution for today. LNAPL is, so when I ask what it is, that means not just what does the abbreviation stand for, but what is it? So it stands for light non-aqueous phase liquid. An example of a LNAPL is gasoline. It's light, meaning less dense than water. So when gasoline gets onto the surface of soil, it will go down until it finds groundwater, and then it will float on top of the groundwater and very slowly start dissolving into the groundwater or evaporating into the soil vapor. What's the other kind of NAPL besides LNAPL? D, dense. And dense will sink to the bottom of an aquifer. Negative consequences of grease discharge. Well, for one thing, it can clog the pipes because during a low flow time, the grease will stop and it will get stuck in the pipe, and then other things will stick to the sticky grease, and you start to lose flow capacity through the pipes. Well, the grease and oil isn't corrosive, so I probably wouldn't say corrosion. Because the pH of greases and oils isn't necessarily acidic. I mean, it might be, but it isn't necessarily going to cause corrosion. Clogging is the one that you can count on. What's the name of the equipment used in primary treatment? Settling? Yeah, it's a clarifier. Okay, now this is a little complicated one, the F to M ratio. Okay, so yeah, low ratio means you've got lots of bacteria, not enough food. So why does that mean you're going to have less sludge volume? They use up all the food, right. And beyond that, they start to eat each other too. Bacteria cannibals. And so there's left body mass, there's not as much body mass because the bacteria are on a diet and they are consuming each other as well. So then that means there's not as much solids that has to be disposed of. Yeah, that's right. That's a good point. So he's asking, the sludge is coming from the bacteria. The substrate is dissolved. The BOD is dissolved, and we can't settle it out through gravity separation. So we get the bacteria to eat the dissolved BOD, and they turn it into something that can settle, which is their body mass. And just like we can gain weight by drinking dissolved sugar, Pepsi, even though Pepsi is a liquid, if you drink it and have too many calories, then you get extra body weight. And so the bacteria are doing something similar. They are eating a dissolved food and turning it into something that we can settle in the clarifier. All right, so those were 8 questions just to get you in the mood to study. And when I see you next time, you won't be in the mood to study anymore, but you'll be ready to get it all out on paper. One last question? Yes? Since you won't have computers with you, we're not going to do anything with Excel, but sometimes I can think of, like, I'll give you a table and ask you to interpret the table or fill in a couple of calculations, but which equations are those? We're talking flow equalization basin? Yeah. A lot of equations for the flow equalization basin? I don't know if that's a lot of equations. Each column has one equation with it, right? So how many columns are there? 6 or so? I think you should be familiar with flow equalization basin, but we're not going to do an Excel problem on the exam. All right. I'll see you next time. Send me an email if you've got any questions, and I'll be happy to help you.